Hey, what's up guys? It's Nicola from Calcunic, and today we're going to be talking about Fermat's little theorem. Let's get right into it. So Fermat's little theorem reads as follows. For all prime numbers p and integers a not divisible by p, we have that a to the p minus 1 is congruent to 1 modulo p. These three dashes just mean congruence, and basically you could think of congruence as saying that the remainder when dividing a to the p minus 1 by p is going to be equal to 1. Furthermore, from this theorem we get its corollary, that for all prime numbers p and integers a to the p is congruent to a modulo p. And if you don't know, corollary just means a statement that follows from. So this corollary follows from Fermat's little theorem. You see we can get to the corollary by multiplying both sides of the congruence by a in Fermat's little theorem. What's going to be important is that in Fermat's little theorem, a is not divisible by p, and for the corollary, it just says integers a, so we don't have to worry about that divisibility. Now, let's see if we could apply our new knowledge of Fermat's little theorem in some examples. Our first example is asking us to find the remainder when dividing 2 to the power of 83 by 11. At first glance, this problem seems kind of impossible unless you're trying to guess, and it's unlikely that any handheld calculator can give you the answer of 2 to the power of 83. So how do you solve this? We're going to start off by using Fermat's little theorem. We could recall that Fermat's little theorem, or FLT for short, is a to the p minus 1 congruent to 1 modulo p. In this case, our prime number that we're dividing by is 11, and a is 2. Since 2 is not divisible by 11, we could use Fermat's little theorem in this case. We're going to have that 2 to the 11 minus 1, which is the prime number, is congruent to 1 modulo 11. Or simplifying, we get that this is equal to 2 to the 10 congruent to 1 modulo 11. Now our goal is to somehow work with this number and make it resemble 2 to the power of 83. Our first step is going to be taking both sides of the congruence and putting them to the power of 8. So this will look like this. We have 2 to the power of 10 to the power of 8 congruent to 1 to the power of 8, and once again modulo 11. Well, 2 to the 10 to the 8 is just 2 to the 80, and 1 to the 8 is just 1. So 2 to the 80 is congruent to 1 modulo 11. Now we're going to multiply by 2 to the power of 3, so we could get 2 to the power of 83 eventually on the left-hand side. So on the left-hand side, we have 2 to the 80 times 2 to the third is congruent to 1 times 2 to the third, and modulo 11. Well, on the left-hand side, since we have a common base, we just add the powers. We get 2 to the power of 83, and on the right-hand side, we have 1 times 2 to the third, or just 8. So 2 to the power of 83 is congruent to 8 modulo 11. And so now we can conclude that the remainder when dividing 2 to the power of 83 by 11 is 8. Our next example is asking to find what is 2 to the power of 14 plus 4 to the power of 42 plus 5 to the power of 13 plus 11 to the power of 26 modulo 7. Once again, at first glance, this problem seems really difficult to solve. However, with Fermat's little theorem, we could take it apart piece by piece. Our strategy here is going to be to try to use Fermat's little theorem for each of the elements in this question, and then bring that all together to make a simplified equation. So let's start off with 2. Using Fermat's little theorem, we have 2 to the power of 6 is congruent to 1 modulo 7. And just a quick reminder, the 2 to the power of 6 comes from 7 minus 1. Moving on to 4, we have the same thing. 4 to the 6 is congruent to 1 modulo 7. Again, with 5, we have 5 to the 6 is congruent to 1 modulo 7. And finally, 11 to the power of 6 is congruent to 1 modulo 7. And all of this is by Fermat's little theorem. Our goal now is going to be to take the terms in the equation above, such as 2 to the power of 14, and to express it in terms of 2 to the power of 6. Well, first let's look at 14. We have that 14 is equal to 2 times 6 plus 2. If we look at this in terms of powers, we have that 2 to the power of 14 is equal to 2 to the power of 6, all squared, times 2 squared. And a quick check will show us that this, in fact, does equal 2 to the power of 14. We have 2 to the 6 squared, which is 2 to the power of 12, and times 2 squared. So we add on 2 and get 2 to the power of 14, as desired. We'll take a similar approach for the remaining terms. We have 42 is equal to 7 times 6. We have that 13 is 2 times 6 plus 1, and finally 26 is 4 times 6 plus 2. Putting this back into the equation we're looking for, we have that 4 to the power of 42 is 4 to the 6 to the power of 7 plus 5 to the power of 6 squared times 5 to the power of 1 plus 11 to the power of 6 to the power of 4 times 11 squared, all modulo 7. Now, from Fermat's little theorem, each of these occurrences of some number to the power of 6 are going to be congruent to 1 modulo 7. Now, this is all congruent to 1 squared times 2 squared plus 1 to the power of 7 plus 1 squared times 5 to the 1 plus 1 to the power of 4 times 11 squared, all modulo 7. Now if we do some further simplifying, we have 1 squared times 2 squared is 4, plus 1 to the 7, 1, plus 1 squared times 5, 5, plus 1 to the 4th times 121, 11 squared, which is 121. Modulo 7. This is congruent to, and just by adding these up, we get 131 modulo 7. And some quick mental math will give us that this is congruent to 5 modulo 7. And there you have it. We've taken a huge equation, as the one above, and simplified it to something really small thanks to Fermat's little theorem. Okay, let's start with our final example. We're being asked to prove that x to the 11 minus x is equal to 7 minus y to the 10 has no integer solutions. Now, you may be curious how to use Fermat's little theorem in a question like this. I think I had a similar question come up in a homework assignment once, and Fermat's little theorem was definitely not one of my first choices for proving this. However, we can notice that we have x to the power of 11 and y to the power of 10 on either sides. So maybe we could take the congruence modulo 11 of both sides and see if we come up with any interesting properties. So how we're going to solve this problem is first we're going to look at the left-hand side, take its congruence modulo 11, and then look at the right-hand side and take its congruence modulo 11. If they have different congruences modulo 11, then therefore this inequality is impossible. So let's start. We have the left-hand side. We have x to the 11 minus x. Now we could use the corollary to Fermat's little theorem on this term here. If we're taking modulo 11, we know that x to the power of 11 is congruent to x minus x from what we had before, and x minus x is equal to 0 modulo 11. And this again is by CFLT, or the corollary to Fermat's little theorem. So therefore we have that the left-hand side is congruent to 0 modulo 11. Hopefully the right-hand side will be congruent to a different number. Now we have our right-hand side expression. We have 7 minus y to the 10 modulo 11. Now before we had x to the 11 and modulo 11, so we were able to use CFLT. However, in this case we have y to the 10 and modulo 11. So the only way we could use Fermat's little theorem is if 11 does not divide y. We're going to look at two separate cases, one where 11 does not divide y, so we could use Fermat's little theorem, and one where 11 does divide y. So for our first case, we have 11 does not divide y. So we'll write out the right-hand side, 7 minus y to the 10, And by Fermat's little theorem, this is congruent to 7 minus 1. And 7 minus 1 is just 6 modulo 11. Once again, this is by Fermat's little theorem. Now we look at case 2. Our second case has 11 does indeed divide y. So if we have 7 minus y to the 10, and if 11 divides y, then y to the power of 10 is congruent to 0 modulo 11. So we have 7 minus 0, which is congruent to 7 modulo 11. Now, we have that the left-hand side is 0 mod 11, and the right-hand side is 6 mod 11, or 7 mod 11. And so, therefore, x to the 11 minus x equals 7 minus y to the 10 has no integer solutions. Thank you guys so much for watching. If you had any questions about the video or other video suggestions, drop them down in the comments below. And if you've made it this far, consider liking and subscribing. It really helps me grow my channel and grow a bigger audience and hopefully help more people out with math.